So can you see my screen?
Yeah, we can see your screen and we can hear you. So
Okay,
yeah,
cool.
take it away then.
Okay. Hello, everyone. I'm so glad to have such an opportunity to introduce our framework to you. My name is Chaoqiang Zhao, and my team is MonoViT, and I'm from East China University of Science and Technology. And this work was finished with a colleague from University of Bologna. And this paper was published on 3DV, and we revised the framework to the Monocular Depth Estimation Challenge. The presentation consists of 4 parts. Firstly, we will introduce the baseline called MonoViT. Monocular sequence-based self-supervised framework consists of 2 parts, depth CNN for monocular depth estimation and post-CNN for 6 degree of freedom post estimation. During training, only monocular videos are used to train the networks, and the supervised signals are built based on the geometry constraints. We all know that CNN-based network suffers from the limited receptive field, which will make the network cannot get an accurate estimation. For example, if the network can only infer the depths locally, it will be hard to get accurate depths for the car and the wall. But if we can infer the depth from a global view, it will be easy to distinguish between the car and the wall, thereby getting a reasonable depth estimation. Therefore, the motivation of the paper is how to get the feature globally and how to accurately model the relationship between objects and how to model different scale objects consistently. From the model level, of course, we want to get a model with better accuracy and generalization. For this challenge, since the training and testing datasets of this challenge are different, the generalization ability of the depth network is also important. Therefore, we introduce transformer into the depth network. As shown in the figure, we use both CNN and transformer in the encoder part to get more effective features from monocular images. CNN block is used for local feature extraction, and the transformer block is used to model the global features. And then both the local and the global features are fused together. From the attention map, we can find that MonoViT focuses more attention on the surround objects background when compared with the sorter method, which means that MonoViT can take more reasonable feature for the depth estimation task. Finally, the proposed framework achieves outstanding performance on the Kitty dataset. As shown in the bottom right figure, the model can get a finite-gain estimation results, which is also important for this challenge to get a clear and complete age estimation. For generalization, we also test our MonoViT model on driving stereo datasets with 4 different weather conditions and the mixed 3D datasets. Our model also shows better generalization than the sorter method for the large-scale objects. And our framework also shows more accurate depth estimation for the large-scale objects. Therefore, because of the impressive generalization ability and the finite-gain estimation ability, our framework is very suitable for this challenge. Then I will introduce the pseudo-level generalization method used in our method. Only use self-supervised training method is not enough to get a satisfactory ranking for the challenge. So we followed previous works that use pseudo labels as additional supervision for the monocular network. But the labels are not ground truths, but retrieved from learning or geometric method. We take inspiration from the reference 3 and distill labels from a previous trained stereo network. Differently, we want to completely avoid the need for any kind of ground truth depths, either on real or synthetic images, by training the stereo network itself in self-supervised manner. Therefore, for this purpose, we can select any stereo network and train it with volumetric loss. Specifically, we select rough stereo and replace its original sequence loss with a sum of volumetric term and a disparity smoothness term following monodepth 2. But for the challenge, such training method is not enough because it cannot get a sharp edge estimation. For those occlusion regions, we cannot get reliable self-supervision. For example, the reprojection loss cannot be properly minimized because of the lack of image content on the red image. This makes the trained stereo images inaccurate on the image left border and at depth discontinuities on the left of the foreground objects. To compensate the missing regions on the occlusions, we explored a third complementary image during training, collected from a viewpoint placed on the opposite side with respect to the right image. On such an image, the regions being occluded in right view are always visible and can provide meaningful supervision when using photometric loss as shown in the figure. Regions that are occluded in this new view are usually visible in the original right image. Thus, the training is constructed on a dataset featuring stereo triplets, and we adopt the minimum reprojection loss computed between the center left and center right photometric terms respectively, together with the smoothness loss term. We train raft stereo on the multiscopic dataset containing about 1,200 stereo triplets for about 1,000 epochs. And the final model is directly used to distill pseudo labels on the KT dataset, specifically for images belonging to the training set without any fine-tuning. As shown in the right figure, the supervision from stereo triplets allow for distilling sharp and accurate pseudo labels even at occlusions. Then I will briefly introduce the supervisory signals used in our method. The depth network is based on the MonoViT architecture, which had been introduced before, and the post network is based on the ResNet 18. And the stereo image sequence from KT dataset are used to construct the training process, so that the supervisory signals are constructed based on the stereo sequence and the pseudo labels. Only one RTX 3090 is used for training, so the batch size is set to 4. 3 losses are used in the training process, including the two widely used self-supervised loss by following monodepth 2, called view reconstruction loss and smoothness loss, and a pseudo-label based loss, which computed the absolutely error between the predicted disparity and the pseudo labels. Then we'll talk about the results. Our methods shows outstanding performance on image-based depth index and H index. But for the point cloud index, there's still a big room for our framework. Besides, as shown in the table, the pseudo levels can effectively improve the performance of the network on different resolution on KT dataset. Then we will show some visualization of our model on the challenge dataset. As shown in the figure, although the test set are different from the KT training dataset, our methods can get a finite gain depth estimation results with clear edge. And the geometric structure of the object are accurately estimated. This is the references used in the work, and thanks for your attention. And both our paper and the code are published online. If you are interested in our framework, you can find more details in the paper. Thanks.
Great, thanks. So yeah, again, if we have any questions from the audience or from the online chat, then just let us know. Again, in the meantime, maybe I'm also happy to start with one. So for the MonoViT architecture, is that pre-trained on any other data set, like for example, ImageNet, or is it just trained from scratch on the depth?
We use the weights pre-trained on the ImageNet 1000.
Okay, cool. Because yeah, that was also one of the things that we in general found, is that a lot of times just including this pre-training helps to improve the performance quite a bit. And meanwhile, other papers that propose these new architectures like PACnet don't actually provide models that are pre-trained on ImageNet. So it kind of shooting yourself in the foot slightly, but yeah, good to know then. But yeah, cool, very cool ideas, very interesting ideas of adapting that stereo network as proxy depths. And I think we have one question in the chat.
Do you think the use of pseudo levels and any limitations to the generalization of the model, or do the other losses help to counteract that? Actually, we do not explore the effects of the of using the pseudo levels in the generalization ability. But as shown in the ablation study, the use of the pseudo levels can help the network improve its accuracy on KT dataset. Since the stereo network is not trained on KT dataset, I think maybe it do not affect the generalization of the model very much.
Cool. Well, I think that's it then. We can again thank the speaker.
Thank you.
And I guess that concludes the workshop. So thanks everyone that attended, either in person or online. It's great to have these discussions and see that people are interested in these concepts. And again, just trying to move away from Kitty and move to these more general scenes. And again, just as a reminder, we will be organizing the follow-up challenge basically in a few months for CVPR. So if you're interested in participating, then keep up to date with our Twitter or our websites where we'll try and update things. But just thanks again, everyone, for attending. And hope to see you soon then.